Alright, so let's talk about directional derivatives, which is sort of interesting that they bring it up here in the exercises because this is really important, and especially if you've taken Calc 2 or Calc 3, you've probably talked about directional derivatives and spent a lot of time on it because this is an important topic. But in this textbook, I guess the fact that it's not super, it doesn't take a ton more work in order to introduce. The proofs aren't super difficult, so they didn't feel it was necessary to put it as a separate section in the textbook. They just threw it in the exercises instead. And a lot of the following exercises seem to use it. So let's introduce it. So here we have this definition of what a directional derivative is of f at a. And so the first of all, what we want to prove is that, well, this should be sort of, if we expect the directional derivative to sort of match our intuition, basically you just choose a vector x, and the directional derivative is the derivative in that direction, then if you're moving in the direction of the ith axis, then that should just be the derivative with respect to the ith coordinate, which is exactly what we need to prove here. So, suppose we have this point A, and we'll call it A1 through AN. Then, if we look at DEI f of A, this is by definition the limit as t goes to 0. Now I need to write the 1 over t out front just because that way I have room to actually write everything. And then in the numerator, we'll have f of a plus t times ei minus f of a. Okay, so what does this actually look like? So this is the same as, I'm going to switch from t to h so that it looks like the limit that we usually use for this. So we're going to have 1 over h. And now f of a plus t times ei. So t times ei is going to be a vector which is 0 for almost all of the coordinates, but the ith coordinate is going to be t. And so if you replace it with h, then the ith coordinate is going to be h. So what we have here is that if we take a plus t times ei, which here it's going to be a plus h times ei, then most of the coordinates are just going to be a, j, except for the coordinate I, which will be ai plus h times 1. So it's just h. So it's going to be f of a1, and then once you get up to the ith coordinate, you get ai plus h, and then you end at the nth coordinate. Then we subtract f of a, and of course f of a, this is f of a1 through an, and this is just the definition of the derivative with respect to the ith coordinate. And so that's what we wanted to prove, and so there we go. Now for b, we want to prove that if you have a constant multiple of the vector with respect to which you're taking the derivative, you can pull that constant out. Okay, so dtx f of a is by definition the limit, and now we're already using the variable t, so we can't use the variable t in the limit, so we'll use h instead, which makes sense because that's the variable that we usually use. Then we're going to get f of a plus, now we take h and multiply it by the vector tx minus f of a. Okay, so now what we're going to do is we're going to let m be h times t. And so if h is going to 0, then m is also going to 0. So this is the same as the limit as m goes to 0. Now we've got 1 over h, and h equals m times t. So I guess everything that I'm doing right now is for t everything that I'm doing right now applies if t is not equal to 0. If t does equal 0, then if you look at the... oh, Jesus. I just broke my pen? Maybe? My stylus? I hope it's not broken. Oh, thank God. I was like just messing around with it and I like pulled the tip out. But thankfully I guess it just goes back in. Anyways, so if t equals 0, then this second thing that we've written here is just f of a minus f of a divided by h, and so that's 0. And that's going to be 0 times dx f of a. So this is trivial if t equals 0. However, if t is not 0, then we can divide by t. So we have this 1 over h out front, and h is equal to m divided by t, assuming t is not 0. So 1 over h is the same as 1 over m over t. So that's t over m. And then on the inside here we have f of a plus, and now h times t times x. H times t is m, so this is mx minus f of a. And so now we can bring this t out front, and then we're multiplying by the limit as m goes to 0, 1 over m times f of a plus mx minus f of a. But look, this limit is just dx f at a. And that's what we wanted to prove. And so we're done. Alright, so now let's do part C. So we want to show that taking the derivative in the x direction of f at a is the same as taking the derivative of f at a and evaluating it at x, which sort of makes sense if you think about it. Because in both cases, a tells you where you're taking the derivative, and x tells you what direction you're pointing in, essentially. That's the idea. So we start this. If x equals 0, then dfa of x is going to be the same as dx f of a because they're both going to be 0. Otherwise, if x is not equal 0, then we have 0 equals the limit as h goes to 0, 1 over the norm of h, and here what we're doing is we're using h as the input of the function f. So this is different from what we were doing before. When we were using h, h was a scalar constant. Here h is a vector, and it belongs in Rn. So that's why we need to have this norm here. And then we're multiplying by f of a plus h minus f of a minus df a evaluated at h. And so why is this true? This is true just by the definition of the derivative. Okay, so this is correct. I had to take a little bit of a break because for some reason this always really confuses me. I think it's mainly just the way that derivatives are presented in this textbook. I guess it's more abstractly correct to begin by defining the derivative as a linear transformation which satisfies this property, and then to later on prove that, this linear transformation is precisely can be expressed by this particular matrix. For some reason it still really confuses me, because just starting with that Jacobian matrix, I think just using that and that itself makes much more sense to me, but whatever. So yeah, so this limit is true, or this equality here is true because f is differentiable at a, so this derivative exists. And this is literally the definition of the derivative. It's the linear transformation which satisfies this equality. And so now that we have this holds as the vector h, which is a vector in Rn, goes to 0. So what we can do is we can rewrite h as t times x, where x is a fixed vector and x is a fixed vector and t is just a well, here let's write it in this way. The limit as t goes to 0 as 1 over norm of x times t. So basically what we're doing here is we are replacing h with x times t. And this is okay because as t goes to 0, x times t goes to 0. And so we're replacing h with 0 we are replacing h with x times t. So if this limit on the left here holds as h goes to 0, regardless of what this sequence of h's looks like, in particular holds if you allow h to be of the form x times t, where x is a fixed vector and t goes to 0. And t is just a real number. So df of a, and now we have tx here. Okay. So now this is equal to, we still have the limit as t goes to 0. Let's see here, okay. So what we're going to do is we're going to, okay, so I'm going to actually use 2 lines for this. So limit as t goes to 0. We're going to have 1 over the norm of x. We're going to keep this here. Then we're going to multiply by, now on top we're going to have f of a plus tx minus f of a over t. Basically what we're doing is we're bringing t inside the absolute value, and because t is just a number, we don't have to be too cautious about how we're using the absolute values. It just works out really well. So now what we have is we have df of a at tx. And remember, dfa is a linear transformation. It's literally a matrix. So if you have this constant t being multiplied by x, you can bring that out front. So we have t times dfa x, and then this is going to be over t as well. Basically, I've just taken this, I've divided by t and then broken up that fraction. Okay? And so now what we have is we can bring this 1 over the norm of x out front, and we can bring the limit inside this absolute value. So we have the limit as t goes to 0 of 1 over t times f of a plus tx minus f of a. And this limit, and we're subtracting, well, the t's cancel, so we just have dfa x. Thus, the two things on the inside of this absolute value sign must be the same, because 1 over the norm of x is non-zero, and this product is equal to 0, so this difference of two things must be 0. And so the two things must be equal. So dfa x must be precisely equal to the limit as t goes to 0 of this thing. F a plus tx minus f of a. And this is precisely dx f of a. And that's what we wanted to prove. or at least that's part of what we wanted to prove. Then, lastly, we want to prove that this linearity thing. Dx plus y f of a is equal to d f of a at x plus y, and this is because this is literally what we just proved. And then because of linearity of the derivative, we have df of a x plus df a y, and then we go backwards and use the previous thing again to bring the d underneath, or to bring the x and the y's underneath the d, and so we have dx f of a plus dy f of a. And that's what we wanted to prove. And so yeah, this is, aside from me having some confusions just because of, I don't know, whatever roadblock I have in my head that sometimes keeps me from making these exercises as easy for myself as they probably should be. This isn't really that difficult of an exercise. There isn't really too many tricky things going on. This last part C, was a little tricky, and I had to look it up a little bit, but it's really, you're not really doing anything. Like there's some algebraic manipulations that you have to make, but that's really all you have to do. Other than that, it's just most of the stuff is straightforward. What's more important here is the fact that this shows us how we can actually work with directional derivatives and define directional derivatives and actually do things with them. And so that's about that. And so we're done with this exercise.